all the elements under consideration that we're talking about is called the universal set. And so that's why if you look up in your Venn diagram here, you see the U in the upper right corner. This is all the elements in the sets that we could be talking about. Sets A and B are specific here. All right, so let's start to take a look at some examples here and see how we do this stuff. In example one, let's consider the sets A, B, and C. Set A has elements 1, 2, 3, 4, and 5. Set B has the elements 2, 4, 6, 8, and 10. And set C has the elements 11, 12, 13, 14, and 15. Let's find the intersection and the union of those two sets. All right. Well, let's go ahead and do that now. First, for the intersection of A and B, let's just take a look here before we write things down. Notice here, A has all odd numbers in it, B all even numbers in it. So in example one, part A, the intersection of A and B is empty. It has no elements. Another way to write that for the empty set is to put a 0 and strike through it, the empty set. All right, because A and B have no elements in common. Now, let's go ahead and look at the union of the two sets now in part B. For the union, we want all the elements that are either in set A or set C. All right? So think of what that is. Set C has these elements 11, 12, 13, 14, and 15. Set A has the digits from 1 through 5. So we can just go ahead and start to write those down. 1, 2, 3, 4, 5, and then 11, 12, 13, 14, and 15. All right, so there's the union of sets A and B. Okay, now in slide number 9, we want to talk about the complement of sets. That's different than the union and the intersection. We can say here that if U is a universal set and A is a subset of U, then the complement of set A, denoted by, notice the notation here, we write down the set, here it's A, and then we use a superscript of a C there. All right, a superscript of a C. So we say A complement for that. All right, so the complement of set A, denoted by A complement, is the set of all elements that are not in A. So notice here in our Venn diagram, here's set A. So the complement would be everything not in A, all this blue area that you see out here. Everything that's in the universal set that is not in set A. So notice down here our set builder notation. A complement is equal to the set of all X such that X is not an element of A. All right. So having said that, let's try another example here. Here we have the same sets we had before in the previous example. A is the whole numbers 1 through 5. B is the whole numbers 2, the even numbers 2 through 10. And C is the whole numbers 11 through 15. And it says here that the universal set in this case is the set of all X such that X is a whole number from 1 to 15. All right, and let's write each of the following. Okay, first we want the complement of C complement in part A. That's everything that's in the universal set that's not in C. All right, so let's go ahead and do that part first. So we want C complement here. Remember that C was those whole numbers 11 through 15. So we want everything that's not that. So that would be what? 1, 2, 3, 4, 5, 6. So really just the whole numbers from 1 to 10. That would be the complement of C. Now, let's move along to part B here. Part B is asking us to find look at this now, it gets a little more complicated, doesn't it? We want the intersection of B complement and C. All right, so to do this one, let's first write down what B complement is, and then we'll do what's in common with C to get that. Okay, so first, B complement is going to be equal to, well, let's see, we're going to exclude those even numbers 2 through 10. So that would be 1, 3, 5, 7, 9, 11, 12, 13, 14, and 15. So we want to find out what's in common with that and set C. Well, let's see. That would be, let's see, 11 would be in that's in common with both of them, so that would be in the intersection. Same for 12, 13, 14, and 15. So there is B complement intersect C. All right. Now, let's take a look at the notion of cardinality of sets now. In slide number 11, we can say that the number of elements in set A is called its cardinality. All right. So the number of elements, the number of numbers, so to speak, that we have in a set is called its cardinality. So we're saying the number of numbers, the size, so to speak, of a set is called its cardinality. And notice the notation we use it. We put n of A, meaning the number of elements in set A. So notice the properties of cardinality here in slide number 11. If A and B have common elements, then the number of elements in their union is the number of elements in A plus the number of elements in B, but then we want to subtract off the number of elements in their intersection. The reason we want to do that is if you didn't, we would be counting those elements twice, and our number of elements would be incorrect. So to find the cardinality of the union of two sets, we take the cardinality of the first plus the cardinality of the second minus the cardinality of their intersection. Now let's say the two sets are disjoint, property 2. If they're disjoint, they have no elements in common. So their intersection would be the empty set, and the cardinality of the empty set is 0. There's no elements in it. So property 2, if A and B are disjoint, then the cardinality of their union is simply the sum of the cardinality of the individual sets. The third property, the cardinality of a complement of a set, in other words, A complement, is the cardinality of the universal set minus the cardinality of set A. So the cardinality of a complement is the number of elements in the universal set, take away the number of elements in that set A itself. And like I said, property 4, we mentioned this before, the empty set has 0 cardinality. All right, so let's take a look at an example now where we use these properties here. So in slide number 12, we have example 3, and it says the number of American households in 1997 in the Midwestern and Southwestern U.S., measured in millions, whose household incomes were below or above